So welcome everyone, and thank you for attending another First Friday virtual Oberlin Acoustics Workshop seminar. Today we have Evan Davis, and he was the acoustics expert and guru at Boeing Aircraft for many years. And now that he has retired, he has gone back to his original love, which is musical acoustics. And we've managed to draft him into investigating and researching violins and cellos, not just the guitar. So Evan is going to talk about measuring instruments and the effect and things you need to look for with microphone placement. So Evan?
Okay, so this is going to be fun and games with microphones. And we'll kind of look at some of the problems and some of the trade-offs in using microphones. One of the things you will find out once we start working with microphones is people like Jim who like to work with admittance and do a mechanical measurement, get away from a whole bunch of interesting, complex problems. So we're not the first ones to run into microphone measurements. In fact, room acoustics and how it interferes or supports the acoustic signal really became an issue in the 1920s when radios started happening and broadcast. And the question of that day was, why does the ear accept the dynamically compressed, band-limited, noisy mono radio signal that's being broadcast into a small room with a loudspeaker as being the same as the music being played in a concert hall? Harry Olson, who ran RCA's laboratories and developments, was kind of puzzled by this situation and pretty much abandoned it and said, I'll tell you how to make microphones and loudspeakers, and why the system works is a little beyond me. And we'll dive into some of those issues. So the first experiment I would ask you to do, not right now, but after this talk, is put some music on in the living room with loudspeakers, walk around the room, try and think about two questions. Does the volume of the sound change much with position, and does the tone color change with position? We've all done that experiment kind of casually. Do it a little more seriously. This is data. I'm running a loudspeaker, running noise through it, and that's the kind of black curve due to a near field microphone to that sound source. And then you'll see two stars on the backs of chairs, which are the frequency response of what that black line looks like as measured at those seats. Now, those seats are where we sit to watch TV and listen to music, and we don't think we've got a problem, but the microphone seems to. So when we talk about microphones, we need to kind of work within a framework, and the framework here is going to be a microphone measurement is valid. It measures what it measures. It is what it is. But to make those microphone measurements comparable with changes to a system, we really want to be able to say that we have a repeatable measurement and preferably a reproducible. So repeatable means basically when you set up your equipment and rerun the experiment, you get the same results. So if you can't do this and you're looking for changes, then every time you see a different test result, you don't know if it's because you can't reproduce your tests or if you've actually seen a change. So repeatability is extremely important. You need to be able to get the same results when you repeat the test with your rig. The next level is reproducibility, which is other people will get your results when they repeat your test, but in their facility with their equipment. What the data means is a very different question in this. This is just trying to get the test procedures reliably. There's a article that Jim and I wrote a number of years ago on how to test, and that's on one of his web pages if you want to get into more details of what we mean by reproducibility and repeatability. So the data from the test they showed for the living room is kind of set up this way, and this is for people who are less familiar with spectrums. And the idea is fundamentally, imagine you're going to sweep through the frequencies with a sine wave oscillator, a pure tone. I'm going to drive our loudspeaker, and I'm going to put a reference microphone, because I'm only using microphone measurements in this talk, as my kind of source reference position. And I've got a roving microphone. In this case, that would be the microphone that was either at Deb's chair or my chair, the dog chair or the other chair. we would sweep up the frequencies very slowly. And to do this slowly allows the system to stabilize. So as you put an impulse into a system, the system rings down. We want to do this slowly enough that we catch all the little bits and pieces of high frequency, high Q resonances, slow sweeps. In the days of Carlene Hutchins, they were using machines that actually had a gear drive that drove the change in frequency along with the plotting pen at the same rate. If you sped up the system, you would smooth out all the little ripples. If you slow down the system, you'd get the peakiest of the peaks that were there to peak out. So when we start looking at sound with our eyes, our vision system is going to be a bit of an issue. Part of this is what our eye likes to see or look at is driven by evolution, not sound plots of noise signatures. So there are tendencies of things that will catch our eye. And if we didn't have them to look at, we may not even be aware of them. There have been a number of studies in sound quality engineering where spectral features that were very prominent were eliminated by redesign and made matters worse, but the peak was definitely not there in the spectrums anymore. So the top plot here is showing the two microphones overlaid with each other. They track more or less in the same manner. There's a kind of a humpy little thing here, and there's a little bit of a humpy low frequency thing. And just to make things a little more visible, we can adjust those two things, split them by adding a offset to the data. Now we can kind of track those two frequency response functions. And this is kind of typical. In the high frequencies, we get a lot of jitter, but these shapes are tracking each other more or less the same. Low frequency, we have more well-separated features. And our eye will typically kind of go, oh, that must be something, that must be something, this must be something. Gee, there's something interesting there. It's just the nature of the way our optic systems work. The bottom plot here is kind of interesting in that what I've done is taken the difference of those two microphone positions. So this is the blue minus the orange, or the orange minus the blue. And so the plots are essentially mirror images of each other. In the high frequencies, they tend to track with kind of a downward slope here and a little upward slope being mirror images. It's down here where our eye becomes something we have to be aware of. That orange peak will strike most people as being something significant. This blue peak here will be seen as something significant. Its mirror image, the valleys, typically get ignored by the visual system unless you're consciously looking for them. So this is going to be kind of a recurring theme in looking at the data sets is we're trying to build some intuition on what we're seeing and what's important. And our eye has its own idea of what's important. And depending on how we make the measurement, different things will pop out at us. So I want to explain kind of in a simple idea of what's going on with the room acoustics here. So we have a source in a room which has got a hard floor. And what will happen here is we have a direct sound wave that's coming off the source, but we also have one that hits the floor and bounces back up. And that can be modeled as having an image source here. And everything we're going to talk about here is omnidirectional microphones. If you have a directional microphone, this gets even messier. So this is the simple version. If we're very, very close to our source here, there's a little bit of an influence of the reflecting plane, but because the level here is very much higher than the reflected level, it's a little bit of a ripple. As we move out, we develop ripples that are deeper and spaced a little bit differently. We've moved very, very far out. These things start to get longer and longer away. If we go really, really far away, then the travel distance between these 2 points don't interfere very much, and we have kind of a stabilized far field type of response. So for fun, I said, okay, let's go demonstrate this in two spaces that I have available to me, my backyard and my living room. So the top line here is our reference microphone, which was very close to the loudspeaker. And then I've got positions that are basically doubling in distance from this reference position as I move further away. In the backyard and in the room with that first position, I get a drop in level and I get a little bit of a messy function here. I drop further away, I get some more humping, But by the time I get down here in the further positions, which are on the order of about a meter or so, the room is kind of stabilizing into a jingle jangle thing with just kind of a mimicking shadow of what's going on here in the backyard. Backyard measurements and almost any measurement you will make, somewhere along the line, there's an ambient noise floor. I live in a city and there's a highway over the hill from me. So that's kind of the ambient noise beyond which I can't really make a measurement. The backyard has pretty hard packed soil and a little bit of grass over it. And so I get a pretty distinctive interference pattern in only the one direction, and the image model kind of accounts for it quite well. Whereas in the room, I've got image sources due to all my surfaces: floor, ceiling, right wall, left wall, forward wall, and back wall. So it's a more complicated system. Welcome to microphone measurements. So with the living room acoustic summary, how repeatable am I? Well, I get pretty good results if I repeat my test, test from the same location, measure to the same locations. I don't move the furniture around. I can get things a little bit better if I move a little bit closer to the source. Repeatable. Will others get the same type of results I've got in my test? I'd say probably, because rooms are kind of rooms and absorption coefficients in rooms are relatively the same. So it's bounded in that we're still in a room, but it's probably awful if we start looking at details. The scatter in the data is probably no worse than measurement position variations in the same room, which we just showed you is a number of on the order of about 20 dB. And what does this mean for our measurements of instruments? Well, it's going to be hard to separate source features from room features in almost any type of microphone measurement without doing some careful measurements and judicious response things, which is what we're going to jump into next here. So this becomes kind of the classic question of even playing with spectrums at any level is, can we see what we hear? And so if I came up to you and said, hey, I've been listening to some nice cello music, would you like to see it? And I say, well, here's the spectrum, and the peaks in the spectrum here are telling all of us basically what notes are being played. It's not telling us when they were being played. We don't know if this is a high peak for this one because it's a very efficient radiator from the instrument, or the guy hit that note many, many times. This corresponds to this time trace, which is the tracing of the recording. And so all this information is in the time trace and in the spectrum a little bit different. And then, of course, our standard music notation. So those people who are really good at reading these plots will see my joke that the time signature in the spectrum was Yo-Yo Ma playing some Bach suites. And of course, the lead sheet here is from the Duke Ellington tune Sea Jam Blues. So let's dive into measurements in a purposely messy space. I thought about this long and hard about where to make these measurements and where to kind of draw the examples from. So this is my shop space in the basement. It's a concrete floor with a rug over it. The window gives you an idea of how high the cement walls go around it. Workbenches, size of a small bedroom. I'm going to take a look at 3 microphone positions. The green one here is on the top of the green pillar, and I'm calling this my room measurement. It's about 1.5 meters away from the red microphone, which I'm going to call my outside the box. It's basically on a stick extending off the fingerboard. So if you're going to mimic this with a setup instrument, think about that microphone being essentially in the strings, kind of held in with some Velcro or something like that. And for Colin, I decided I would put an inside microphone in here and take a look at it. The positions of the inside and outside microphones are essentially mirrors around the top plate. So I tried to set those microphones up so they're equally distanced from the bridge island area. My striking implement, what I'll talk about a little more, is a little tap hammer here, and we'll show you a better picture of that in a moment. So I did all these measurements so that I have 2 measurements for each one of the environments. So I'm doing these in pairs, and I'll talk about that in a moment. The blue here is the inside microphone. We get a really big A0, and it's more powerful response in the low frequency end, which is kind of expected. Here are the repeats for the 2 microphones that are in the red position. They're a little bit tighter, so it says there's something about the inside measurement, which was a little more sensitive to the way I was striking it, and that may make sense. And the green one here is the green room. We can also take a look at these as transfer functions. And one of the things I want to point out with transfer functions is we're going to use the red microphone as our starting reference condition and look at the changes relative to being inside the box in the blue and outside the room in the green. Notice that when we do this, a lot of these pointy features, which are really quite evident, kind of get smoothed out, and saying the transfer functions are actually relatively smooth with a lot of jitter over them. So when you do transfer function measurements of resonant systems, a lot of times you lose your resonant frequency markers. So here's what I did. I measured the microphones in sets, and I'm beating on them with a little chopstick here. I bought a new set of microphones that have little power amplifiers in them and has a little bit of a frequency response and polar plot data here, kind of generic. Most of these microphones roll off at low frequencies. Exactly where they roll off depends on exactly how the microphone was made. So this microphone here says things that are below about 50 hertz are rolled off quite a bit. So data lower than that, I need to be cognizant of it. So here's my tap hammer. I also worked with this tap hammer, which is a felted mallet on a drumstick. I was hoping to be able to use this to emphasize low frequencies and then the tip to do high frequencies and tell people what to go by. The tip here is got an odd shape, and so it's harder to make the sound reproducible than using the round ones. So in my measurement sets, I do outside in the room, outside and inside. That gives me two versions of the outside microphone measurement. And similarly with each one of these things, the room and the inside microphone will show up in two. I did taps on the locations of the bridge feet, 10 taps on the bass side, bar side, and 10 taps on the sound post side with the wooden bead chopstick. So showing you the difference between hitting on the bass bar side and on the sound post side. Kind of what we'd hope to see here is the response or in the low frequencies on the bass bar side or higher, the sound post being kind of more of a nodal position in the top. In the very high frequencies, we're in about the same type of position. Something interesting is happening here. Also, when you take a look at these log frequency plots, the eye is smoothing things due to the density of the data. So I took this little section here from about 1 kilohertz to 2 kilohertz, put it on a linear scale. And these big differences here, once again, 6 dB per step. So that's about 18 or 20 dB here. And this is about 10 or 12 dB here, are mapping into this sort of feature here and this sort of feature here. So when we start looking at microphone measurements for analysis or bookkeeping of changes, diving into details, blowing them up, bringing them back down is going to be part of the process. So this is kind of my summation here of tapping with the microphone responses. Since the taps are going to be in both of the microphones that were measured, they more or less cancel out. Whatever problems I had with the source levels or not hitting exactly the same place, I think that the precision of my location on the sound post side is probably an issue, and if I'd done a pendulum tap, I would have been in a better place. The modal frequencies are independent of my drive position and my measurement positions. They're kind of universal properties of the structure. So the peaks that I'm seeing should be in pretty good stability places. However, the relative amplitudes of these modes and hence the relative sound pressure levels are going to be determined by the drive point measurement position and measurement position. So I've left the microphones in the same position, so I haven't varied them. I've done my best with a hand tap to keep the drive points about the same. So the acoustic response here has a couple other things kind of coming in, and there's different ways of describing this. So in the room, like the living room and stuff, there's an interference pattern, and this is going to hide some of the modal response. If you move really in close to the source, you start to see less of the room response, and that measurement is probably on the order of about half the size of the plate. But once you get into that really close in thing, something else is happening. There are a couple of different characterizations of the near field. One of them is called the hydrodynamic near field. And this is a place where the air is sloshing around. So if we're in an A0 type of thing where we have a big flow from the F holes and we have little flows from the rest of the instrument, the air moves out of the F hole, tries to equalize its pressure, so it kind of fills in the areas around the box. So we get a local field which has got a lot of pressure activity to it, but it's not radiating out to the far field. In another point, it's kind of the geometric near field, and this is where different bits of the instrument are radiating in and out of phase, and our modes in these instruments start doing that from the beginning with the V1 plus and minus modes. And so that difference in how their interference patterns set up gives us something called a near field. So the player is definitely in the hydrodynamic near field. The other musicians are probably in this geometric near field. And then there's something that we love to do because the math is really simple, which is the free far field, which is a Mathland idealization or an anechoic chamber. Basically, the idea is we're so far away from the source that it looks like a point, at which point we have a directivity function, which is the output from this geometric hydrodynamic near field activity. So what can we do about the room? One of the things that we can do about the room is take a lot of these points and average around them. So I purposely said, let's do an average that, as far as I know, nobody's really doing with acoustic instruments here. Is I just put a meter stick out. It's about a ½ meter off my reference microphone. And I'm just taking 5 positions, end, quarter, half, 3/4 end microphone positions, and then doing the energy sum to sum them up. And what you can see here is it really helps refine the variation in the very high frequencies, these very large scatters. And once again, that distance here is 8 dB. So we got about a 20 dB margin here, and we're collapsing that down to more like a 6 dB type of bounding. There wasn't a lot of variation in the A0 range. There is some variation here in the B cluster in the cello. And this energy averaging technique tends to drift you towards the high side of the dB plots because those are the places where you have the most energy. So spatial averaging can help stabilize some of the variation we're seeing in the room. And hopefully the features we're seeing here are more related to the source than the room itself is the intent. Let's take a look at low frequency placement here. What we have here is inside the box. For various reasons, we expect a very large pressure signal. Near the inside of the box, so these are the mirrored image microphone type things, as we see a drop off, and relative to what we're seeing in this B complex, they're about even here, and it's more prominent there. And in the room response, the A0 is dropping off. And we typically expect to see something like that down here in the low frequencies, this hydrodynamic near field effect means as we move in, we kind of get into it kind of accentuates the pressure associated with the low frequency features. So this idea of the hydrodynamic near field is air is rushing in and out of the sound holes. Now, this reactive pressure field is also what gives us our F-hole air masses, which is entrained local flow. So we're using the effect of having an acoustic near field to tune the A0 thing. The size and shape of that F-hole will determine how the air is controlled and moving. The local airflow can be seen as kind of like dominating the entire problem and interacting with the other sound sources on the body, kind of overwhelming them. So it looks like, just a simple source at that point. The sound pressure levels in the hydrodynamic near field will decrease quite quickly with distance. So the place where we'd expect to see this kind of bass boost effect is on the order of about maybe 1/4 of an acoustic wavelength. So for the cello, it's about 1 meter, and for a violin, maybe 1/3 of a meter, which is basically saying our player is in this hydrodynamic near field. And that hydrodynamic near field would give a different impression of the bottom end to the player than someone who's in the far field audience. So microphone positions do matter when we're taking a look at the responses of these systems. So one of the things I want to talk about here a little bit is we're making certain assumptions about how useful a spectrum is going to be to us. And we're going to have to kind of own up to the fact that the ear-brain system is very clever. And the ear-brain system is designed to do things that help us survive as animals in the wild. So we have an error correction algorithm, if you will. The prime example here is if someone's talking and then someone coughs and interrupts the signal, we typically are able to kind of hear what wasn't there and complete the message. So by the context of the sentence and our knowledge of the language, we're very likely to be able to hear the message through with interruptions. Part of this is there's got to be some energy in the bands that would have been in the speech to help us do that. But we're very clever at doing that sort of thing. We're filling in details from corrupted or masked audio signals. When we're hearing music and we're kind of concentrating on one instrument, and then we go back and listen to the other one, we kind of think that signal was all there. There's some singers that kind of take advantage of this, where they sing, doo-wop music, and there's only one person on stage singing all four parts. And when you hear the recording, you swear that there are four people singing all four parts, but the person is using this masked, hidden audio thing to give us just enough information to go, oh, I wasn't paying attention, but it was always there. The real thing that we need to be contending with, and Arthur Benaid and other people were very interested in this whole thing, is we can hear through room acoustics. It doesn't take us long before we can feel out the size of the room, kind of know what's an echo, kind of apply information to a direct source. So we kind of hear through this room acoustics, and our microphones are very dumb. They really respond to the room acoustics. So we don't really hear through room acoustics with microphone signals. And that is kind of one of these things that comes into the idea of auditory scene analysis in the theory of hearing, that we do have these capabilities that are hard to build algorithms for. The other thing that's been pointed out, if you read this stuff on hearing and the psychology of hearing, is the language of hearing is by analogy. We typically say things like, it sounds like Bob, it sounds like Jim, Mary, Debbie. Things I've read, Cern says, due to studies that have been done, we can identify probably on the order between 200 and 500 individual voices. These can be the voices of friends and family, but also maybe prominent actors or TV personalities, that we have a very large catalog there. Other sound effects, things that kind of come up when we're talking about instruments, it sounds like thunder, it sounds tubby, it sounds tinny, but it's the sounds like. It sounds like a 1923 $5 Sears catalog violin. The language of vision is quite different. We do train ourselves to identify colors, blue, black, green, and red. So the analogy of doing this sort of analysis with spectrums and trying to look at sound through our eyes does set us up for the vision system trying to do what it wants to do to help give us information, not the oral system. One of the things that's kind of interesting is if you look at sound quality engineering, which is done with manufacturing things like cars and the sound of your dishwasher, auditory scene analysis, which is trying to figure out how the brain really responds to sound, and sound recording, there are only three things that people seem to be able to agree on, which is ranking loudness, pitch, and brightness. And when we are doing spectrum shaping types of studies, spectrum changes are best heard if the signals are equalized to equal loudness. Now, in international standards and psychoacoustics types of things, we use a reference tone of 1,000 hertz. You play the tone, you play the sound that you want to respond to, and you adjust them so that you have the tone at the same level as the sound. And in doing this, people will basically give you an equivalent tone level for things like dishwasher sounds, automobile exhausts, fan noise, airplanes crossing over, and they can all be referenced back to this kind of arbitrary tone. On other types of studies I've been involved with sound quality engineering, a group or an individual making those adjustments. So if we made a number of tap recordings of cellos and we wanted to make sure all the taps were sounding about equal loudness, an individual who's kind of done this a little bit or a small group will drive to an agreement fairly quickly. So there is some hope there. So this comes from the sound recording version of brightness. Is the black line here would be some sort of baseline equalizer. And there's something called the brightness band, which is the upper frequency range. Some people curtail this a little bit different frequencies because they call it harshness, but we'll just call it brightness. So we want to make the sound brighter. So the obvious thing to do is lift that band up. But when we've done that, we've made the sound both brighter and louder. And so we've changed two things when we only meant to change one. The other thing we could have done is left that band where it was and dropped the flanking areas. Okay, so now brightness is coming up, but we've reduced the loudness. So when we're doing these things on spectrum changes, a lot of times it has to be iterative, that we want to see what brightness means to us. When we make these adjustments, we change the loudness. We need to re-equalize for loudness before we look at the spectrum changes. So it's our brain helping us in ways that make the simple analysis more difficult, but it's something we need to be aware of. And we need to be aware of this, particularly in something that is done quite a bit, which is spectrum normalization. We have our basic data over here. We've got the inside microphone, the end of the fingerboard microphone, and the room microphone. And we look at them and kind of go, well, it kind of makes sense. The closer I am into the instrument or put my head inside the box, it's louder and it's quieter out in the room. But I really want to see what the spectrums look like. So one of the first things that a lot of people would do would normalize to the average level. So we've integrated across all the loudness here, and I've just done this on the dB level. There are loudness models Brian Moore has developed that would be a little more accurate to doing this. When I normalized to the average level, some of the differences that we saw that were a little bit big in the interior microphones kind of get washed out. That typically says I must have had a little bit more source level in one of the two measurements there. And here we start to see something nice is that we've got some sort of hill function over here. It's showing up in all three different things. It's showing up with about the same contour and about the same spread. Low frequencies, we're getting a very distinct feature, but the level is quite different relative to the upper level. And here in the middle, it's interesting that we're getting quite a bit different responses between the inside and the outside when everything's balanced out. So normalization here is kind of bringing in places where we've got some similarities and accenting some places where we have differences, which may be a good thing when we're trying to do some troubleshooting. Another normalization that is easy to execute is go find the maximum level and just set that and do everything relative to the maximum level. This can be a major problem in that the different source data sets may have maximum loudness due to different features. So in this case, when I did the inside box, the blue one, its major feature and its major highest level was the A0 level. In the room, there was some sort of high frequency little tick up here at a couple of kilohertz, and that was the high level. And then in the microphone right off the fingerboard, it had a feature that had something to do with the B0 complex. So in this case, you know, are we seeing apples and oranges here by picking the maximum level because they're due to different types of things? So to get around that problem, another choice you have is on this side here is I've normalized to the A0 levels. So I brought all them into alignment so A0 peak level matches up. And now it's almost looking like the polar opposite of this one when we lay everybody up together is now the in the box response looks like it's suppressed, and the in the room levels seem to be accented in the high frequencies. It's all the same data set, it's just adjusted differently. So when you're doing your diagnostics and when you're doing your searches for changes and stuff, realize that the way our brains are working here are going to pick out things differently depending on what set of data we have. And so I think comparing spectrums by normalization is a very useful thing to be doing We need to be very careful about what claims we are making on those. So, microphone position selection. I wanted to talk a little bit about a different way to approach this problem here. Is let's kind of think about who's sitting where, okay? So at the player's ears, a very privileged position. It's very localized. You know, it's not across the room, it's in the close proximity to the instrument. Therefore, it tends to be a pretty repeatable and pretty reproducible type of measurements. There will be variations due to body size, and that includes both the instrument and the player. How are they interacting with the instrument? It's very likely that at the low frequencies, we're going to be in the acoustic near field, and therefore we're going to be sensing something that may not be showing up in measurements that are made further away. In a continuous activated instrument like the bowed instrument families, this is very important because this is the feedback control position. This is what the player has to work with to adjust the instrument to make it do what that musician wants to do. So it's in the feedback loop. So if they're hearing something they don't like, it's this signal that they're going to use to rebalance. So if they think they've got too much bottom end or they're too shrill, this is the position that they're going to have to be working from. They don't have access to what's happening in the back of the hall. The next group of people are the people who are in the ensemble or in the section. And this space becomes very interesting because it is highly variable. You're working in a place where the field hasn't completely developed that will show up in the audience. It's very susceptible to differences in the floor and ceiling reflections. So this becomes interesting with directional instruments. In the practice room, we've got small room acoustics. So we've got all that kind of hash from bashing things around. Your neighbor is sitting 6 feet away from you playing their part. In a hotel room type situation, you've likely got a rug on the floor, so you've got a fairly absorptive floor, and you have a fairly reflective ceiling. In many practice rooms, in musical spaces or classroom type things, like if you think about the Oberlin hall we work in, the hardness is on the floor and not on and it's soft in the ceiling. There's an acoustic ceiling there. So the first bounce, which would be the most dominant one in one room, may be from the ceiling, which means it would be hearing the top of the instrument, if you will. And in another place with a hard floor, it'd be responding to the back of the instrument. So the tone color of the instrument is going to be influenced a little bit by the place that you are in when you're making the measurements. In a concert stage, or in large room acoustics, we typically have a little bit more clean air, if you will, before we get into the jaggedness of the room, a lot more modes being excited. Concert stage design has always been plagued with, can the orchestra hear themselves? Can the sections hear themselves? A lot of early designs were relatively small rooms because it was completely acoustic. Going back into the early time that Haydn's music was written, he was writing for relatively small rooms. In bigger rooms, higher ceilings, multiple uses, like in theaters, you could have a very absorbing ceiling, losing some of the cues and bounce backs, and then modern architectural people have put in new structures to get better room bounce. So this highly different environment for the rest of the playing section who are trying to work together to balance each other is a very complicated and interesting issue. The audience is essentially either in random positions or in every possible position, forward of the stage. It's usually in something that's called the reverberant far field, which means that there really isn't much left of the signal being radiated directly from the instrument. Most of the energy they're getting is being bounced off ceilings and walls. Time delays between early and late reflections can also start coloring what they're seeing. When the room acoustics dominate, it's really the sound power response that tends to be driving that. And that's kind of akin to our space average measurements around the instrument. And all that jaggedness, and we're right back to living with the living room chairs. So, microphone measurement. So why even try? Well, this is kind of internal to our own brains and ears. It sounds like the real thing to us. Many of our computers and microphones are cheap and easy to acquire at this point. So it's a very tempting thing to do. we need to keep in mind that microphones are not ears, and they're going to be picking up information that is physically there that our brains are cleverly removing because it's a correction. It's like, oh, I'm in a room and I'm hearing secondary sounds from other directions that are really kind of pictures of what the original source was. So I'm going to integrate all that and give you an integrated view of what the sound is. This is kind of the room acoustics removal type of thing. So our brains are doing this for us because they're going like, you really don't want to know what the room's doing. You just want to hear what the main source is. We can leverage part of this in today's technologies by using the ear to listen for differences, by recording and playing back the taps as part of the study of looking at spectrum. So in many recording systems now, you're keeping the original time records, playing them back to back. Our oral history memory is really quite short, and so making abrupt sounds next to each other, A, B, a friend of mine who did his career work in studying infant hearing and other cognitive things goes, this is Sesame Street. What thing is not like the others? Can you hear the changes? I find that I can hear quite a bit differences between instruments by just kind of flacking my thumb against the surface. It's great. I can hear differences. I can identify things as being different. What does it mean to the radiated sound when the person plays an instrument? I don't know. Eyes will have to be trained to see sound in spectrums. Because our eyes are looking at that data in a different way than our ears are, our eyes will tend to look at differences and pointy bits. One of the ways to kind of fight this is turn everything upside down. Your peaks become valleys and your valleys become peaks. And so if you look at our data on both the cello and on the violin, there are some very stable valleys that tend to be overlooked. And if you flip it upside down, it's going like, wow, there's these big peaky things that are always here. They just draw your eye differently. So measurement main points here is this is a temperamental measurement. In my career, I was working with broadband noise signals that had multiple sources, the sound inside an airplane in flight or in a flight deck. Even though all that jingle jangle stuff or room acoustics is there, it tends to average out over fairly wide bands. And so when you start looking at narrow band phenomena, this stuff gets magnified and it makes things a little more difficult to interpret. The repeatability of microphone measurements, however, can be quite good. You need to develop your process that is repeatable, and that's going to be basically set up equipment, making things as repeatable as possible. And also, it's a good idea to test in multiple environments. So if you're testing with a rig that has microphones relatively closely spaced, test in different environments. Go test it in your bathroom and then test it outside. Those are probably going to be your extremes of a reverberant environment and a relatively anechoic environment. If those environments aren't influencing your measurements very much, you're probably got a fairly stable type of system. Reproducibility in every international standard. Repeatability is always going to be worse than reproducibility. Everybody using their own tools in their own ways can usually get repeatability down. But if you sit there and do round robin testing, which is usually circulate some sort of test standard between labs, the reproducibility usually is pretty sad relative to what the repeatability is. In doing round robin testing, hard lesson learned in industry is you want an indestructible standard test object. So instead of passing around a Stradivarius violin to everybody to test, this is probably a good place where if a composite or some other really stable instrument may be a good standard test object to compare between different measurements. There are trades to be aware of, and these primarily deal with positioning the microphone array. If you move in close, you'll be defeating the room acoustics as much as you possibly can, soft floor, that sort of thing. However, you're introducing yourself to the non-radiating near field acoustic pressure field. And I think for player positions, putting a microphone where the player is going to really sit there and say, yeah, even if they're in the near field, that's going along and moving with the instrument. And this one's for Colin, of course. We can move inside. Well, we're defeating the big room acoustics, but we're introducing the small room acoustics. The small room travels with the instrument is kind of the argument that's being made, and I agree with that. However, the data gathered on the inside has some different characteristics from the outside, and so there's a learning process here to be able to interpret the interior room acoustics measurements with the outside, and that's true of any of these measurements. Is you need to be able to make your mechanical measurements and look at the acoustic measurements at the same time. Space averaging averages out the room acoustics to response to a certain degree. A lot more measurements are needed. And in doing this, you're kind of hiding the sound source's directivity functions. And that may be important when you're trying to figure out how to balance the instrument between the audience and the section. In loudspeaker design, Floyd Toole ended up doing a central array, which was basically in the forward arc, about 30 degrees cone. You made lots of measurements in that area, and so that's the important thing. It varies, but if that one is controllable in that zone, it's in pretty good shape. The nice thing about loudspeakers is we usually know where they're being pointed and who they're being pointed at. In musical instruments, the directivity patterns are scattering around the room. And in many cases, we don't know who our primary audience is. If you're the soloist and you're pointing your violin in a certain way towards the audience, or if you're in a section and other people need to hear you. Lots of very interesting issues. So want to come into something called something completely different. We're calling this the trap of expectations. And I think this is really pertinent to microphone measurements. We have a history that we're involved in. I mean, it's setting up the way we think about a lot of these problems. So expectation number one is it'll all be clear once we look at the spectrum. And the idea there is if we know where the frequencies are, we know what their levels are, and we know how peaky those levels are, or what the damping is, we've pretty much got it. So Saunders in the 1930s did glissando testing with violins. And I think he's one of the earlier people kind of looking at this and kind of de facto saying the spectrum will tell me the difference between a good and a bad violin. If you read his early papers, it almost sounds like he thought this was going to be a weekend job. He was asked, can you tell the difference between a good violin and a bad violin by testing? And he said, it'll be in the spectrum. Give me a couple of good instruments. Give me a couple of lousy instruments. I'll get back to you next week. And of course, we're still working on this problem. Carleen Hutchins and John Schelling, of course, worked on plates and then B1 tunings, A0 tunings in the instruments. Once again, saying, if we get these things in the right positions, we should have a pretty good idea of what's going on. Dunewald did relative spectrum levels in bands. And I hope if you think about the different measurement positions I've given you, that if you're not measuring in the same place as Dunewald was, the spectrum shape contours could be different enough that you would need a different system of bands and different level indicators to know what's going on. So this is the whole thing about normalizing spectrums and saying, okay, I've normalized the spectrums. They're all about the same energy levels. And now I'm going to look at the relative levels of different features in those spectrums. If we're measuring on the inside, that's probably going to look like a different map than if we're measuring on the outside of the instrument. I'd also like to note that many of the sound radiating characteristics that drive sound radiation efficiency are wideband in nature. And they typically are associated with something that may be much lower frequency peak. This is another talk at another time, and this is really the development of loudspeakers and how loudspeaker design evolved by kind of suppressing, if you will, the lower frequency peaks, over damping them so they weren't a major carrier. And most of the design of loudspeakers is in this high wideband pass type of behavior. The other thing that we have kind of in expectations, and this is kind of the idea of if you just change one thing at a time, you'll figure out how the whole system works. The problem is with mechanical systems that we're working with is if you change one thing, you change everything. Something's going to change in every part of the band. You can't just isolate one thing. electronically, like some of the work that Jim Woodhouse and Claudia Fritz have done is, if you have the acoustic signal and you can go filter it in electronics, you can essentially change B1 minus frequency range and not change the high frequency performance of the system. Mechanically, if you change one of those, you'll change the other one. Once again, when you're doing this, your eye is good at picking up changes, and that's going to be helpful. But it's going to look for hills and trees or the peaky bits. So when you're doing this sort of study, turn the picture upside down. So talking about expectations, we talk about the voice of an instrument. And the question is kind of a philosophical one. Do we expect to be able to identify an instrument in the same way we can identify a human voice? I guess we're ready for questions, Van.
All right, thank you, Evan. So I think we should start perhaps with more specific questions about microphones, and then we can gradually evolve towards more broader questions that's raised by this last slide. I'm happy to go until as long as people want, so we might go until 3 o'clock. So, so the floor is open for questions now. Oh, one thing what I'm going to do is I'm going to actually also create a couple of breakout rooms if people want to have their own little private conversations while they're on this. And so you can text somebody and have them meet in your own little private room for a private conversation if you want. Okay. And questions. Oh, use the raise hand function. Any questions? Come on.
I have one.
Joseph?
Yeah, when you were talking about the hydrodynamic near field, let's say you are measuring, I don't know, 5 different violins with the microphone within, what was it, 30 centimeters roughly. Would you expect that because instruments are so similar geometrically, that it's consistent to do one? In other words, they're all going to behave kind of the same way within that near field position, or do you think one might differ from another drastically, but that won't show up there?
Yeah, I mean, I think the the hydrodynamic source that we're most concerned with is actually the air coming out of the F holes. And so that flow dominates, almost all the instruments. We don't have like the back pumping more than A0. So I would think that being in, the same position, you're measuring the same type of effect. The range of it, changes with wavelength, but the wavelengths aren't changing much as you retune A0. They're all real big relative to the instrument. So I would expect it to be reasonably stable. If you had something that, if you moved around the instrument and you had something that was dipping out, which would be showing that there was a second source that was also very large, that would be an indication something has changed. Most of the time, when you have a hydrodynamic near field, is that airflow is moving around the instrument so much that it basically becomes this really simple source. And the simple source physics kind of takes over, and you've got a pretty uniform field. If you're measuring right on top of the plate, as close as you can possibly get, you may get some contamination by local motion of the plate itself. So, this thing's kind of flowing and it needs to equalize itself. So it needs a little space to work in.
Okay. And if I can add on to that, let's say you're trying to measure the instrument as the player hears it. Would you tend to take several microphone positions, and average them? People hold their violin in different ways. So would you tend to take an average of a bunch of these?
I think taking an average would help stabilize whatever room effects you have too. Mm-hmm. But the distance between our ears isn't all that much.
Whoops. I think we just lost Evan. Yeah, okay. I think we lost Evan. Hopefully he will get back to us.
That's
Meanwhile-
a disaster because I wanted to or to sharpen Joseph's question. Because
Okay.
I think, but, oh, there's Evan. Okay, Evan,
Yep.
I want to sharpen Joseph's question. I think what he meant, or what I understood interesting there, is if you're doing on the same shape instruments near field measurements, do you expect those changes between instruments to correlate with some brain impression in the audience? Or is it very far away? I think that's what you want to know. Is this a useful measurement?
Yeah, I think it's a useful measurement, though it's a different measurement. Okay, so
It's different, but we're then going to look at differences between instruments.
right,
And
right.
whether those differences correlate with the thing you really want to know.
Right. So the, assuming that A0 is just pumping air out, it's the volume of air that's in phase versus out of phase. And so if we assume that those two parts are walking together because we haven't changed the F-hole design much, I think a near field measurement could be extrapolated to an outside measurement, given that we know that structure. If you have an unknown source, the near field pressure is harder to, unilaterally say, I know how to relate near field to far field. If we have very similar devices, I think that transfer function would be fairly stable.
Yeah, the special point here is that almost all of the violins look identical to something.
Oh yeah,
like
yeah, and A0 doesn't move around much in frequency.
right.
And our
So
F-holes aren't. I think if you look at A0 as a pumping mechanism, it has a long tail as a monopole. It's a very small source, and so I think it carries through. And one way you can look at these low frequency features is A0 kind of sets a platform, and the other modes add and subtract from that. I've done that with louds, with guitars, though I use the main plate mode as the primary monopole, and I'm thinking that was my my expectation as a mechanical engineer. It's the structure that's more important than the air part of the system, and I would reconsider that at this point.
Guitars have more variety of what they look like, the geometry.
Yeah, but you'd be surprised on how stable their mode placements are.
Sure.
Yeah, let's that was Professor David Politzer's, and he raises a very interesting question. I'm not going to get into this now because there are other people who have raised their hands, but I think we want to come back to this topic about how different are instruments versus the spectrum. But first, let's get to George Stepani, who has had his hand up.
Hi there. Thanks for being so sensible. It's nice to keep us trying to keep our feet on the ground a little bit when we get into this stuff about sound. But the thing I wanted to pick you up on is about very early on, maybe the second or third slide, you were talking about transfer functions and saying that they tended to lose your frequency markers. I didn't really quite understand what you were talking about. Can you just unpack it a bit for us?
Yeah, let's. I take it I'm still sharing, right?
Hey,
Yes.
see it. I see it.
Yeah. Okay. Where were we? I think it was up here. Yeah. So we're up here. So take a look at it. Take a look at A0 here, right? So what's happening is if you take a position between the red and the blue down here, that distance and that distance are about the same, right? So in the raw data, you see this A0 resonant really, really clearly. But because these two lines are running kind of in parallel, when we look at the transfer function between the two of them, they're relatively constant. I mean, you don't see the sharp features.
Right. I see. Is this a common technique for looking at this kind of measurement? 'Cause I mean, it's
Well,
it's a concept of the transfer function between the hammer force impact and a microphone response.
well,
So that, of course, the hammer tends to be kind of uniform response, and
right,
the reaction to it isn't.
right. So getting back to kind of the question about the near field measurement versus the room measurement, right? So if we take the pair of the red and the green curve here, sit there and say, if I take the information that's in the red curve and extrapolate it out to the far field, there's a very simple generic transfer function between the two of them here. Okay, and it's basically saying that there's kind of a general trend, if you will, between the transfer between the two of those, with some jitter due to basically the room acoustics. So the use of transfer functions is more in extrapolation than it is in analysis. You have to be careful when you normalize your data that you may throw the baby out with the bathwater, right? So if you normalize these data sets here, and they're all got, you know, peaks of about the same magnitude relative to their floors between the two of them, when you take the difference plot, they disappear. So
Okay,
in
I see what you're doing now. Yeah, I
yeah,
understand.
and
So basically, they tend to converge at the higher frequencies, but there's a very big difference at the low end. So the internal measurements strongly emphasize the low frequencies,
right,
and the far field emphasizes the high frequencies relatively.
right.
Yeah, okay.
And with the interior measurement here, because this becomes a volume velocity, it's volume velocity that radiates, but it's the net pressure change, the volume displacement here. This sort of trend in the inside to outside level, you know, makes sense of that model. So, you know, so that you would expect a smooth curve that wouldn't respond to the resonances in that transfer function in math land.
Okay, thank you.
Thank you, George. Next is Jesus.
Thank you, Fan. Hi, everyone. Ivan, can you hear? Okay. I have a question about recording directivity patterns. It would be possible to measure, for example, the directivity pattern in the critical frequency effect for a violin, like 3 or 4 kilohertz, without an echoic chamber. I mean, in a room without some proof in the walls. It was clear, my question?
Yeah, so directivity functions stabilize in the acoustic far field. And so you typically have the geometric near field where different parts of the plate are out of phase, and that gets picked up as the precursor to the directivity function. So directivity functions can only be cleanly measured in kind of anechoic environments and at a fairly far distance away from the source. The physics of the geometric near field is setting that up. It's that interference pattern as you get further away, when the travel distance between the 2 points of the plate are essentially the same, you know, so you're far enough away that isn't coming into effect. So these near fields are typically places where the travel distances between the 2 parts of the plate are different. So directivity patterns are great, but they're really a far field type of measurement. And when they get brought back in as a prediction tool, you know, loudspeakers and simple sources, it kind of works, but with complex bending systems, it's a little more difficult.
Okay, even thinking in high frequencies with short wavelength, even taking account all your suggestions about improving our measurements, the answer still being no.
Yeah, because if you think about the high frequency thing, all they've done is shorten the wavelengths.
Mm-hmm.
And the geometric near field is basically the difference in the travel time or, you know, where you are on the wave. And so if you had, even if you're at high frequencies, if you're one end of the instrument to the other end of the instrument, there's quite a bit of difference in the wavelength, the distance traveled between those 2 points, which is giving you the interference field.
Okay, thank you.
Yeah, the kind of the good news is the more little bits that are traveling, so you have more and more little humps on your plate, this interference pattern becomes very, very complicated and tends to self-smooth to a large degree.
Okay, my last question. Then in a anechoic room, we can measure, or do you think that we can measure the critical frequency effect of radiation at 0 degrees?
Well, critical frequency is kind of an infinite system behavior. And on arched plate type systems, it's typically going to be a smeared region. It's not going to be a discrete frequency. And so you can usually see it to a certain degree in radiation efficiency measurements. Acoustically, it's usually relatively hard to see unless you've got a really large clean plate, because all the scattering that happens with the motion around the edges is the field hasn't really, the modal field is kind of dominating the radiation instead of just the simple traveling wave thing of critical frequencies. If you do the simple model of a simple plate with a single drive point, what usually gives you an idea of where the critical frequency is, that's where the treble will start rolling off. So it would be parts of the, so there are ways of kind of understanding what may be going on in there, but it's really not such a clean system whenever you have a real system that has discontinuities into it.
Okay, thank you.
All right, Andrew Brown.
Unmute yourself, please.
Hello.
Hi.
So thanks for the talk, and thanks to Jay Vanderkuppel for inviting me. So I've done some work on double bass acoustics, and I wondered if the experts would care to comment on the near field and the far field acoustics of the bass. It's long been my theory that the room acoustics are somewhat more influential with the timbre and sound quality of basses, you know, the perceived qualities because of the long wavelengths. And I'd like to know what you think.
You can't get in the far field of a bass is basically where it starts. You know, the wavelengths are very large. You know, in the room measurement, one of the things that, you know, would be, I can do, I probably should have done, but would be fun to do is, you know, take a bass and bring it into a bathroom and take out all the fluffy stuff in the bathroom. And now you've got, you know, 2 rooms, the inside room and the outside room. And I would expect that you would see the influence of both rooms. The bass itself, you know, I did some calculations a while ago and said, okay, how big a room should I be testing in if I use international standards? Okay, and so I think with the violin, and I'm doing this from memory, so this is a little gamey, but I think for the violin, it was like you could probably get away with something about the size of a 2-car garage. And for a cello, I think I needed a basketball court. Okay, and for a double bass, you know, I needed a stadium, you know, to get far enough away from it. And so I do think, especially in both any of the bass instruments, you know, the cello and the stand-up bass, is you're definitely in the hydrodynamic, you know, near field. And so my favorite experience of being in a very strong near field thing was playing with a gong, very large gong, about 6 foot diameter. And we were allowed to play with this thing, and you're up close to it and you're banging it, and you can hear waves shimmering across it, and you can hear things bouncing as the waves run around the thing. Just amazing, you know, and you're just like totally mesmerized. You can understand how people use this as a meditative device. And then you have someone's, you know, you're waiting your turn and you're 12 feet away from the gong, and all you hear this is some stupid guy going bong, 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 getting none of the impressions. So yes, I think the bass is, you know, a completely different animal due to its, you know, wavelength and sizes. That said, though, is a lot of the pitch information we're getting off the bass is kind of more in our normal audio range. And so, there's an envelopment feel of playing the bass close in. I'm a drummer. I have the same thing with a bass drum. I have to tune my bass drum to the room, to get it to ring right and not sound odd. Rest of my drums, I'm fine with them. I just carry and move them. So, yeah, there's a very strong low frequency effect here. And I've got an Engelhardt bass. I've got a real high end bass.
Right. Well, thanks for taking the time for that question. Mhm.
Yeah, actually, on that interesting subject, we do have Anders Boen here because many years ago, Knut Gutler did some research into the interactions of the bass with the floor, the stage floor, and I think Anders was a part of that study. Anders, are you on?
Yeah.
Do you have any comments on that? I know I'm
Well,
putting you on the spot here.
yeah, I was participating in the measurements, and I kind of was the guy with the instrumentation. So I was there, of course, and we tested in a smaller concert hall at the Norwegian Academy of Music, and we tested. What we tested was, is there an effect of radiation from the stage floor taking part of the experience for the listeners? And Knut and Anders Askenfeldt, which were the main thinkers, they have the opinion that it does. The floor makes a difference and influences the very lowest frequencies from the double bass.
I could also comment on that. So I spent much of my student career and professional career as a bass player in Vienna, and the players are quite picky about which spot they would like to have in the Musikverein on that stepped stage, and that's part of the effect. And I find it interesting that these traditions go back many years when they are only now being scientifically described.
Yeah, we're probably only scratching the surface with this, but I've done more analysis to that floor, and there is a heavy floating floor under there, and it has the resonance frequency around 30 hertz, an octave below the main zero resonance, and I think that is the main reason for the response of that floor. And we tested several wooden floors in the new National Opera House, where some of his students were playing. And we also tested the orchestra rehearsal room, which they didn't like so much. They liked the orchestra grave floor better. So,
So thank you.
And there's another effect here that I'm going to go back to, is this bouncing off the floor. This is your bass close to the floor but not touching it situation. So a lot of the work that Anders was talking about is the end pin is in connection with the bass, and you have a mechanical connection. So this would be like a floating source here. You can see this sort of interference pattern over hard soil. So there's an acoustic image source of the bass that's very close to its primary source, and so there's this sort of behavior coming in the acoustics. Even if there wasn't a mechanical connection to the floor, the height of these valleys and peaks would depend on the impedance of the floor, which is something Anders was talking about, the different floor constructions. So there's both the mechanical connection to the floor through the end pin, and there's also this acoustic field situation going on. So, yeah.
Yeah, and they had the opinion, at least Knut had the opinion that maybe the effect is most easiest heard or best heard by the players, and not so much by the listeners.
That's typical of a lot of these near field effects, is they don't propagate out in a way, but they're They're very important to the person holding the instrument, and they're the ones that are in the privileged position again. They're using it to control the instrument.
Okay, thank you, Andres. Colin?
Yeah, thank you. Fine talk, Evan. Enjoyed it very much. And it was nice to meet Andrew on the bass, because I've been particularly interested in measurements on the bass as well as other instruments. And one of the advantages of the measurements inside the instrument, of course, it's independent. The size of the instrument is defined, well defined, and you don't have to worry about the room acoustics at all. And it's particularly important for the larger instruments. But I'd like to go back to what Evan's, I think you called it slide 3. It's fine actually here. As the microphone measurements as to what it is. I'm not totally clear how the measurements were made, and you're not using a hammer or a way to excite it in a definite way, or is it being excited? Exactly how is it being excited, in fact? You said you were tapping it with the drumsticks, essentially.
Right.
But therefore, how can you get anything like reproducibility from different measurements? And so how can you, perhaps you'd like to answer that one.
Sure. So first of all, by trade, I'm a drummer. So I am pretty good at reproductive tapping, and I trained myself on this for a while before I recorded.
Right.
I'm tapping it at locations, and I'm listening to the volume and consistency of my taps. Okay, so I am going to agree with you that this is an unmeasured, who knows what I really put into it, other than looking at the spectrum levels and looking at the time signatures. I'm very consistent across. And my argument for consistency, let me see if I can get a picture where this is a little bigger. Oh, this will work. So in the fact that I have two microphones, I'm comparing with each other. So I'm going to take a pair of, red and green, and I'm going to tap. So when I'm looking at their relative levels, they are both polluted by the same tapping mechanism. And since I've taken, room and the outside and the inside and the outside, I've got two measurements of each one of my microphones. So if you look at the green and the red here, you'll see that there's two different colors of green, and they're just very small differences between the two of them. Okay.
Yeah.
When I did the interior one, and these are paired up with, one of these is associated with one of these red curves, and one of these is associated with one of these green curves. I could look that up for you. But relative to the repeatability I've got in these two curves, I've got a bigger difference in the inside one. I suspect that the inside one, for whatever reason, may be a little more sensitive to how I tapped. I don't know. Something to look into. But these curves here would sit there and say, I was pretty repeatable if those two raw data sets are lying on top of each other.
I agree about that.
Yeah. And so when I sat there and said, well, maybe I should do more different taps, but I said, with my health checks on these, I was like, I can't right now say I've chased down why the blue curves separated on the order of about 5 dB relative to the fraction of a dB, 1 or 2 dB on the other ones. But, to this audience, as I want to say, okay, I was hand tapping. I've got little white markers, which are about 3 times the size of my hammer. I'm reaching across. If I did a pendulum swing, could I improve that? Probably. If I had an instrumentation hammer, that may have told me I was, off kilter a little bit, but that's what I did on this one, just microphones.
Fine. Thank you. The one thing, could I comment too, while that slide is up, it's very interesting to see the comparison on the cello of the 3 different types of measurements. And clearly you can see the very strong correlation at low frequencies between the inside measurements and the outside measurements. Difference in heights, as you said, are to be expected on theoretical grounds. But I think there's a very strong correlation overall, I think you would agree, with the generic variation with frequency of the plots, even out to the high frequencies, up to 5K, I believe.
Right. So
the one thing that I'd like to comment at the moment about sound measurements, these are measurements in a given direction. It's let's call it the forward direction. One can see at high frequencies, there's huge amounts of fluctuations, which tend to get averaged out at the higher frequencies, but they're still there.
Yeah.
And one of the things about averaging things out is that you are averaging out the peaks and troughs of the response. And it's those peaks and response which give a lot of the fluctuations of the partials when you play with vibrato, for example, and they extend right up to the high frequencies. And by averaging out, thank you very much for coming to the slide, you can see you're averaging out those fluctuations. Now this worries me because when you're playing the violin, of course, even when you're playing the lowest notes, you've got something like 40 partials, all harmonics of the lowest note that you're playing. And the sound that you're hearing is not just the note as everyone will understand, it's not simply the note that you're playing at that pitch. It's all these partials that the ear is cleverly putting together to be the sound of the instrument, whether it's a violin or a cello. And as soon as there is any fluctuations in frequency, you will actually get huge variations because of these peaks that are in a given direction that give the liveliness to the sound of the instrument. And I think one's, in a sense, losing that information when one takes averaging of any sort of the spectrum. And when one listens to a violin or a cello or any instrument, you can actually tell to quite a large extent where the instrument is being played, even in a concert hall. And you're sensitive to the first echoes and first sound that comes in within about the first 35 milliseconds. And so since you can tell where the instrument's coming from, it may well be that you can actually tell something about the quality of the instrument too, in that 35 milliseconds, as it were. And well, it slightly worries me that if you lose a lot of the information that's coming out from averaging of spectra, which is nice for presenting the overall performance and intensities of things, but you may be losing something that's very important in terms of the actual tonal quality that you hear as a listener. That's the comment rather than the question. Sorry about that.
I'm not
Okay.
disagreeing with you. This sort of plot, one of the things about, showing as much data as possible, is the background colors give you a pretty good sense of what the underlying variations are. And then the average curve here gives you an idea of kind of the overall shape of the system. So, the fine details are important, but they can be overwhelming. And I think this is one of the problems with visual analysis of information, is it's a balancing act.
But the ear is very clever because it's listening to every single one of those partials and integrating what it hears on all those partials to give it the quality of the sound that you're actually hearing of the instrument itself. And so it seems to me that the fluctuations are actually an important part of the tone of an instrument. And if you have an instrument that would completely flat, it would be very uninteresting at all. A flat in response, that is.
Back to Max Matthews' experiments early on.
Yeah.
Yeah. Yeah, you need something to get that vibrato to have some character to it. I agree.
Could I just add a
Okay.
comment on that one quickly, just while you've got this slide up? Colin, don't lose sight of the fact that most of the wiggles in those curves are from the room acoustics, not from the cello. So here's a question for you. If someone plays vibrato, no, sorry, if someone plays without vibrato, but you shake your head at 5 hertz, you will get, your ears will be receiving the fluctuations. Do you hear the brightness, the liveliness effect, if you let the room acoustics make the fluctuations rather than the cello body? I think that's quite an interesting question.
But it's an important question. It was examined in the 1990s, I think it might have been. Certainly the room acoustics, because it comes back in different phases from the echoes, interferes with the direct sound that you're hearing, and it interferes with it, and you get a very complex sound that it actually involves as much the instrument as the room acoustics. And that's one of the particular features, the complexity of sound at particularly at the higher frequencies, that gives the violin its rather special quality. That I mean, a little bit of vibrato, and it only needs a tiny bit of vibrato to go up and down those very narrow peaks, basically. As you said, the minimums may be just as important as the maximums from that respect.
Do you hear the ones from the room acoustics as well as the ones from the instrument body? That's the question. Most of the fluctuations you're seeing there are from the room acoustics.
That's probably right, but you do see fluctuations of a similar nature if you look at the inside sound. You see very strong and large fluctuations like that and inside sound as well. So certainly the effect is important intrinsically from the instrument itself, but I agree entirely that the room acoustics will actually affect the sound of an instrument.
Yeah, in fact, I think you can see the extent of the room acoustics, this being the room microphone. I'm getting, my hash down lower in frequency than the smaller room, if you will, here. Yeah. And so, thinking of the room acoustic density of modes sliding down is, yes, we get a small room acoustic feel at a different place. So if I put a pendulum microphone inside the cello, do I get a better vibrato? That's kind of your question, I think, Jim.
Yeah.
The answer is yes, you would. I mean, the point is that the air inside the instrument is just part of the instrument itself, as is in fact the near field that vibrates with the plates in and out, just bounces in and out as the plate bounces in and out. And the near field and the field inside the instrument are every part of the instrument as, shall we say, the tailpiece or the neck or something like that. And we're talking about all these peaks are modes, what we call normal modes of the instrument itself, which involve all the vibrations of the component parts of the instrument. And so when one's measuring, for example, the sound very close to the instrument, which is dominated by the near field, the air bouncing in and out of with the plates, it's very similar to, in fact, the sound that you're going to get inside the instrument, except that the sound inside the instrument is going to excite the modes of the inside of the instrument, which are part of the instrument, just like the strings, sympathetic vibrations of strings. It's just the same. They're about the same sort of mass. You've got a few grams, a couple of grams or something like that inside the instrument. There's no different from the G string as an oscillator. It's all just part of the instrument. So that's one of the advantages, in fact, of playing, in my view, of the inside measurements, quite apart from the fact that, that they are insensitive to the room acoustic and external noise. So one is measuring something that's intrinsic of the instrument itself when one's measuring inside sound measurements. And of course, all violins have the same shape virtually. Cellos differ a bit in size, and violas change shape a bit, and double basses. But I mean, it does provide a completely reproducible, for a given instrument, air shape, volume, performance space in which to make measurements. So I could take my violin from my room and take it across to Oberlin, and I would expect to see exactly the same sort of measurements, which is, as Evan was saying, is not so easy when you're complicated by the acoustics of the room that you're measuring it in.
Colin, my only objection to what you say is that the single microphone position wipes out all modes that have a nodal line there. So I think if one took more positions inside, then you've got a better picture of the influence of the air. In fact, then, as you say, the normal modes are the wood and the air inside and whatever else is connected to the instrument. And when you look at the internal air, you're biasing it towards the component that is derived from ancestor modes, say, which would be the modes in a rigid walled cavity.
I agree entirely.
I think the single microphone position is going a little bit too far in a way in cutting out, say, for example, the longitudinal dipole, which is in a sense the second most important property of the box, like in terms of the air and in terms of what happens in the plates. They say volume change, longitudinal dipole is second in importance to the monopole volume change.
Yes, but I mean,
how about a new question at this point?
Okay, yeah, let's go to a new question. Before I get to Chris Dungy, there's been a question on the chat line for a long time now, which is, for recording these kinds of frequency spectra, what kind of microphone is recommended? Cardioid, condenser, ribbon, etc. And how much should I expect to spend on a microphone?
Cup of coffee.
So I'm going to kind of take this in a couple of different parts. Anything that has a directional property to it, like a cardioid microphone or a ribbon microphone, once you have that directional property in, you need to account for that. Okay, so one of the things that will happen with those microphones is they have their own near fields to them. So they will have a proximity effect, and singers use that proximity effect on cardioids to kind of give them a little boost in the mid-range. So all this work has been done with very small lapel type cardioid microphones. What do you get when you spend more money? One of the things I've been finding with these microphones is, relative to instrumentation microphones, is their precision of the devices varies. So with all these microphones, and I bought 3 new ones from the same manufacturer on the same day, from Amazon. So take all 3 of them, I put them right next to each other. I played my broadband source, rotated them so they changed positions, that sort of thing, and said, okay, how close are all of those to each other? The other thing is, with these, I had a little bit of some information from the manufacturer on where they rolled off. What happens with almost every microphone is you need to vent the cavity that's behind it. This tends to give you a low frequency roll off. Now, for violins, a roll off that's down around 50 hertz is absolutely no issue. If you're working with a bass with a roll off at 50 hertz, you're going to be rolling off your bottom end. Instrumentation microphones tend to be far more expensive. They tend to be very clear on their omnidirectional patterns. They do a lot of work to kind of get the vent in the back to be as low frequency as possible. Most of the popular microphones you're going to get are aimed at kind of voice/music. So they have some bandwidth types of issues. If you're looking at things that are, in a couple of dB type of range, the $10, $15 powered microphones that I bought, work quite well. If you're going to be doing instrumentation type work, putting some more money in a calibratable microphone is probably worth the effort. You can cross calibrate. You can kind of find out where these little humps are and adjust your data. So my main point is you want an omnidirectional microphone. I find that certain people advertise things as omnidirectional microphones and then they send you a cardioid pattern for their microphone. So omnidirectional microphones is what you want to use. The lapel microphones are going to be reasonably good for violin type instruments. For the bass instruments, you need to be a little more aware of where they're rolling off the device.
Okay, let's go to Chris Dungy.
Thank you, Evan, for your talks are always really informative. From a maker's perspective, somebody who specializes in cellos and basses, my takeaway is the takeaway is my takeaway correct in thinking that if I want to get repeatability and reproducibility, that I take my measurements internally so that I rule out any room acoustics being part of the spectrum?
We got Colin here and a big advocate of the interior measurement. What concerns me about the internal measurement is positioning the microphone and some features that we're seeing in this range here, in this case of this cello, and it's a plywood cello, it's not nothing special. And so this moves around depending on the instrument. Is your education process is going to be your most expensive process. So whatever measurement you're going to make, you're going to then try and figure out what your target is. What does a good instrument look like when measured in that manner? So your time and effort is going to be in, the stuff that Joe and Martin have done with their rigs and their measurement systems is correlated design changes to the response changes and kind of knowing which way they want to push things. So for, the cello bass maker, yes, the room acoustics are going to be there. If you go inside, as George was saying, you're going to get some balance of things based on what that measurement position is. And so it's going to be a training thing. Are you creating factors in the interior measurement that are related to interior modes, which because you're exciting on the interior have high pressure signals, which are drawing your eye to them, and yet they're not showing up in the radiated field. And that can be handled by education, even though, if you take a look at the inside measurement and the room measurement and saying, well, your audience is hearing that, red is probably closer to what your player is hearing, and this is what's, more unchangeable as you move the instrument into a different environment. So it's an educational process of where to concentrate your efforts. So there isn't a simple answer here. I think the work to correlate your changes to what you want and the measurement, make the measurement consistently and build up your experience base to sit there and say, oh, this has got something going on here, which is a higher level than I would expect on a good instrument. And I need to, modify that. Sorry for the muddy answer, but it's a complicated question.
Yeah, I know this whole subject is complicated. So when you were talking about the lapel microphone working well for violin, and then you alluded to a different type of microphone for cello and bass internal, do you have a recommendation?
I don't have a model number, no. I have bought and used for uses on my guitars and as a musician. I found that some of the more expensive lapel microphones had better frequency response and less handling noise and stability. So most of those came with their own little power module. One of the things I found with some of the off-the-shelf ones, lapel microphones, is they fit easily into a cello and a bass, but I couldn't get them through the F-hole of a violin.
Right.
So
Right.
that's another thing, you know, your design changes.
Right.
When we were doing large arrays for Boeing, and we bought very inexpensive buttons and did all the wiring ourselves. One of the things about the manufacturing technology that's used there is the manufacturers say, well, you're all going to get very similar microphones because either they work or they don't. If they're out of tolerance, they don't function. But we've quickly found out that we were buying probably 3 microphones for every one we used, that each one of them had a little quirk. And so, you know, at the level of 3 dB, you can use almost anything. You want to get much better than that, you know, you're going to have to spend some money, is my recommendation. You can do a lot with a cheap microphone.
And then I just have a couple of comments going back to the stage floor question. For anybody that has attended Oberlin in the previous years when we were meeting in person, I think my cello acoustic tile demonstrated very clearly the input that the floor and the surface that you're playing on has with a cello, and especially with the bass. My other comment is regarding the bass and room acoustics, and that was when I was a judge at the ISB 2015 competition. They were, the tone judges were playing the basses in a way too small room, and I kept asking, can we find a bigger room? Can we find a bigger room? They couldn't find a bigger room. When they publicly demonstrated the basses on a large stage floor, all 3 tone judges immediately commented, these basses do not sound at all like what we heard and played in that smaller room. So my comment is, yes, the space is going to be definitely a huge factor, and especially for the double bass in terms of determining what that instrument's all about. And why I've taken it on recently as a project is beyond me. But thank you again for these presentations.
Can I ask a question?
Yeah, Anders. Anders is next.
Anders, you need to unmute.
Yeah, I've unmuted myself, and I'm going to ask a really stupid question now about the room modes in your measurement room, Evan. I'm sure you know where they are, but I'm very surprised to see that it's a fairly large difference between the green and the red curve there. And my first thought is, could it be a room resonance influencing this? I can see that there's a lot of diffusing room acoustic elements there in the plane, but
yeah. So no, I didn't. You know, I could go down and measure the room. It's you know, it's a bedroom-sized room in the basement. The walls are covered with, you know, the claptrap that all of us people who dabble with stuff are in. You know, so there's on the far wall, on the backside of the cello is a set of file cabinet, wall cabinets with bits and pieces of stuff. There's a rug on the floor. Yeah. I wanted to use this with something, since we're dealing with a lot of people that have relatively small shops. I said, you know, this is a messy environment. You know, that room is probably on the order of 12 or 15 feet in length. It's got an open door. My music room is a lot bigger. And the red position is basically the mirror image of the interior position. So I wanted to get that symmetry in the raw data set. And so, you know, the distance between the red and the green one, I think was like a 1.25 meters, something on that order. It gives you an idea of the scale. Those benches are probably on the order of about 6 feet long, 2 meters long, something like that.
So, do you think is the cello itself large enough to reflect significant energy at say the A0 frequency?
Hit the wall and bounce back. Yeah, it's probably, even at low frequency, it's probably a messy environment. I'll grant you that.
Okay. Well, But I can tell that I do measure room resonances in my own apartment because we deal with boomy floors from neighbors above in some projects, and sometimes they have the same resonance frequency in the floor systems as in the room. So you get a very good coupling there.
This, I mean, the window pane that's behind there is probably resonating somewhere, windows typically go off somewhere around 200 hertz. That's a big sound re-radiator and stuff. So the idea here was this was not a chosen room. It kind of highlights all the possible problems you would have in a usual size, kind of shop room.
Okay, thank you very much. Very interesting.
All right, Jay.
Yes, hi, Evan.
Hi.
I've been thinking a little bit about our testing on the cello in the dance studio at Oberlin.
Yeah.
And one of the things I've been thinking about is, do I want to invest in something like a Lazy Susan for bass? And I was thinking about, does that make sense? I was first concerned about the issue of not getting a good contact with the floor because it's on a Lazy Susan. But then I started to think, since we were rotating the cello around, we were actually in a different room for each microphone position, weren't we? So, do I want to look at something else instead? What are your thoughts about that?
So the thing with the bass, I can go play with my bass and get back to you a little bit too, but the bass is going to be so low frequency. One of the things about correlation of acoustic waves is just think about, can I get far enough away that I actually have a different measurement, right? So think about a beam bending and I put 1 point force on it, right? And I measure near it. So with the wavelengths of the bass, it's like you can't get far enough away from it if you got, the monster wavelength at 42 hertz, that the room itself isn't even really resonant. So the cello at about, 100 hertz or so like that, at 42 hertz and that sort of thing is, to a large degree, you're almost like the room inside the room. Like there's the room inside the bass and the bass is still in a room because, especially in its bottom end, it's still, almost a constant pressure Helmholtzian thing. So one thing that comes to mind, and I haven't ever thought about this, is you can have a Helmholtz resonance between two cavities in one sound hole, right? So think about, two boxes with one sound hole between the two of them. So with the bass, it'd be interesting to take it into the bathroom and sit there and kind of go, okay, now the outside room is 4 or 5 times the size of the inside room. Are we retuning A0 as we move the bass into different rooms? So when you get into the concert hall, it's basically free field again, but in these other rooms, are we retuning the bottom end? I have to go do something for you. This is too much fun. I've got a small bathroom or two, to work with.
But I'll talk with you if it's okay, because
Sure.
I'm a little hesitant to invest in a Lazy Susan for bass, since there's so many problems yet with the idea, and I'm kind of thinking about creating something more like Joe's rig that with kind of a spinning wheels for the microphone to go around rather than to spin the bass around. We'll talk about it.
Yeah, I think the thing with the bass is it's going to be hard to get out of its near field until the higher frequencies, and higher frequencies are important for it. So there's a little bit of work there, but the room is going to be so small that it's the ability to move the microphone so it's seeing a different part of the instrument. So, and we're hearing stuff in the higher frequency range with the bowed string that not all the bass is down in the bottom end, but it'll be, because I think the problem is it's going to be hard in a regular space to get much modal density to help the acoustics differ.
Yeah.
Good question though. Good problem.
Okay, let's go back to David Politzer.
Okay, not unrelated. This comes from book learning. An anechoic chamber is expensive. How about outdoors with the microphone on the ground? I'm a theorist. That should work. Does anyone have any success with that?
Yes.
So the main problem with that is if you want to get a different orientation to the instrument than the ground plane. So, you're getting, basically you've got an image source that you're canceling by putting on the ground microphone, right? And as you move away, you're going to change the angle at which you're hitting your microphone. But it's a shallow angle relative to being like on axis of the plate. So that's kind of your trade there. Yes, you can do that. But what happens is now if you want directivity, now you're going to have to sit there and say, okay, how do I rotate my instrument relative to my ground plane to aim it at my microphone? And when we were doing airplane directivity studies, we use ground plane microphones to good advantage. But of course, we're far enough away that it's a point at that point, even at a low flyover. But I like ground plane microphones, by the way. They really help. But they're limited.
All right. Oh, wait a minute. We have another. Oh, Marty's got. In your background photograph of a long table full of violins, did the judges move along the length of the table? Oh, wait a minute. Okay, Marty, that was for the concert. So they were just put there. And, for those are the concerts we had at Oberlin. And so the musicians were performing in the hall. That's the instruments were just sitting there. Okay. So we're approaching 3 o'clock. Do we want to stop or do we, because, well, let me just throw this out, and we may not have enough energy to actually answer this complicated question, but David Pollitzer hinted at this, and we sort of discussed this issue or aspects of this at the last talk, at the end of the last talk, which is that I remember Evan saying that the first time he saw a graph of an acoustic response measurement graph that Joseph Curtin had made of 10 strads, Evan said something to the effect that if somebody told him those were 10 different measurements of the same violin, Evan would believe that person. So if that's the case, how useful are frequency response measurements of instruments?
Did I say something?
Yes, go ahead.
Related to that, the last question on your presentation, Evan, was, do we recognize violins the way we recognize voices? And the obvious answer is no. We can tell a wide variety of voices apart, and people can probably all say something is a violin. And I think that relates to what you're saying, Fan. The big problem, I think, with violin measurements is it's so hard for people to tell the difference. So it's hard to look for things that are explaining particular differences, maybe brightness or loudness. I think where you can tell different voices apart easily with the violin, it's more like you're trying to tell there's one voice and does that person have a cold or a cough? I mean, we're trying to find little subtleties. So were you going to answer that question? Were you going to say something about the way we recognize voices? I'd love to hear your thoughts on it.
So this kind of gets into a conversation I had with Jim a little earlier on expectations. And so, what are we expecting from any of these investigations? And it kind of comes back to the early stuff that Saunders did, and it kind of comes from Helmholtz and Renwels to Raleigh to a certain degree, is the spectrum does carry some information about the performance of a system. And almost every system has these sort of behaviors. Is in the high frequencies, we get a lot of chatter, but it's kind of statistically bounded. And it's actually reasonably easy to predict. The hill features in violins are a little more difficult than flat plates, but this kind of continuum in high frequencies with subtle adjustments is kind of is what is expected in a mechanical system. Down here, these are usually controlled by the gross properties of the system. So they're usually pretty hard to change. So when I looked at your data, comparing it to like data from beer cans or from cars, is these low frequency things are basically the shape and the weights of the system and the materials used. And so they tend to be very stable. The things that typically happen is something that's called the mid-frequency problem. And here what happens is small changes typically have relatively big influences. And so these typically are characterized by slight non-uniformities. So if I have a flat plate of material, you know, the basic bending stiffness of the plate gives me that mode. The fact that it's plywood gives me this sort of behavior. And here, since it says, oh, I've got a chuck hole or I've got a, you know, a block of wood on it or something like that, that's where those things are changing. So the mid-frequency problem is usually where we're most sensitive. And that also is one of the places where it's hardest to predict things, because typically something changes here and, you know, that little peak comes down, but this guy boosts and this guy's split over here. So these mid-frequency problems are one of the most difficult places to predict. So prediction accuracy tends to be a reflection of that. Is it's like I can be very, very precise in the low frequencies. I can get the statistical thing, the high frequencies with a little effort, and just know that I've got chaos in the middle one. And this is where the fine prediction work, you know, typically has to happen. And also that's where manufacturing variations typically show up. And so looking at your original data set and the, you know, the thing I blurted out, which I'll be quoted for from here to like 10 years after I'm dead, is, you know, looking at that, I said, well, you know, the low frequency things look very stable. They look very, very similar. The high frequency is a continuum of jaggedy type things. That's exactly what I expect. And in those plots, the middle frequency doesn't have very much variation in it. And so I'm going, these look like very, very similar systems. Now, if you look at guitars, and I've done this with data that I've collected on from the literature and stuff, you'll see the same thing. The two lowest frequency resonances are always in the pocket, very, very close. The mid frequencies change, especially in radiation, because the radiation properties flip around a little bit on guitars. And then the high frequency plate stuff is really quite similar. And you don't need to go to microphones to see this. I mean, if you look, you know, Jim's been doing a lot of stuff with admittance over his career, and he'll see the same thing. It's like, yeah, we got some stability thing. Mid frequencies, changes in bracing patterns of guitars or lutes, you know, will change a little bit. If you normalize the frequency response curves by the lowest note you've played, you know, you'll find that in the violin family, there's about a fifth between the air resonance and the plate things. And in a lot of plucked instruments, it's more like an octave. You know, so you can see families of instruments have kind of properties, and that makes them work. You know, why do they all look the same? This comes from, you know, evolutionary ideas on designing instruments. Is the resonances have found the places they need to be to project well. I will make the assertion that the driver for musical instruments has been loudness up until the electronic age. Louder instruments win. And louder can be because you've got more high end. It's, you know, it's like snare drum works on the principle of fooling the ear. I drop the stick on the snare drum and I have the snares off. You get one set of loudness. I turn the snares on, I drop the stick on the snare drum. It sounds a lot louder because there's a lot of high frequency energy there. If you look at the low frequency, I've lost a little bit, but it doesn't matter. I've thrown a lot more energy in the high end. So I think all these instruments have kind of evolved up until the electronic age as being basically loudness wins, and the stability of the design is if you do much to fall off this curve, you know, it's not a desirable instrument. That said, all the other variations are typically probably in this mid frequency range, and these are the subtleties of tone color. And so, you know, we have to work, if you will, to get a really bad sounding instrument. You know, ignore all the rules. We've had a couple of people at Oberlin who don't have instrument building experience, but are good woodworkers who have built, quote unquote, out of the books and end up with reasonably good instruments. You know, things need to be in the pocket. If these are optimized designs, it wouldn't matter where you started, you'd get here pretty quickly. And so if you look at the history of musical instrument evolution, is once a new principle was thrown out, so somewhere along the line, we decided to do arched plates for violin type instruments. And that design locks in very, very quickly. And I know you guys, everybody's messing around. So, 500 years of clever people messing around and we haven't changed the instrument too much. It's a relatively robust optimization, and it's not a particularly sensitive one because wood properties and small changes in construction don't throw it completely out. There's a number of people who've played with circuit analysis stuff on optimization, and people get these systems that have to be completely balanced or else they don't work. So if they're out one part in a 10,000ths, the thing collapses. So this design in almost all of our musical instruments are quite robust to manufacturing variation or material variation within a limited range.
All right. Any other questions?